right? And then your slot angle
Sir.
is electrical is 360, mechanical degrees divided by 360 slots times 10 gives us 10 degrees electrical. And then KD sine G dash psi over 2 over G sine psi divided by 2. That gives us 0.956. AP is cos of epsilon divided by 2, which is 30 divided by 2, is 0.9659. The winding factor is KW, KP, and that gives us 0.9236. Then we have to calculate the flux. And always remember we work per phase, and therefore it will be 650.85, which is 11 divided by square root 3, divided by 2,22, and KW, and the flux, the frequency, and the number of conductors. That gives us 0,086 Weber. And then the full load current is S divided by square root 3. That's 10 mega divided by square root 3 divided by 11K. That gives us 524.86 amps. Any questions there?
No.
Right, then we go to number 2. Oh, let me just, so that this thing is out of the way. Right, so number 2 says there are 3 slots, 3 pole pairs, yeah. G is 12. Remember, that is the number of slots per pole. The pole pitch is 1. There are 40 turns, and the flux is 0.0028 Webers. And the flux, the current in the conductors is 50 amps. Now, if we've got single phase, we want to know what is G dash. That is the slots per pole per phase. Now we've got a single phase, therefore G dash is 12. Then we can calculate psi, which is 180 divided by 12, which gives us 15 degrees. And then if we calculate KD, we get 0.638. And because they talk about turns, it must be 4.44 kW phi FZ. We calculate the number of conductors, which is 12 times 40, divided by 1. That gives us 2,800 conductors. And if we multiply that out, we get 1,142.15. And S is V times I. That gives us 57.11 kVA. Now for a two-phase, for G dash is now 12 divided by 2, which gives us 6. And then if we calculate Z, it is 12 times 60 times 40 divided by 2, which is 1,440. And then we calculate KD, that comes to 0.903. And then E, 4.44 times 0.903, 0.0028 times 50 times 1,400, that gives us 808.28 volts. And then the rating is square root 2 times VI, that gives us 57.16 kVA. Now for a three-phase, remember G dash is now slots per pole per phase, so that's 12 divided by 3, which gives us 4. Then if we calculate the number of conductors...
Sir, can I please interrupt you?
Yes.
Yes, sir. Here, when I'm looking at your equation for the E, I got everything correct, except that when you calculate E, you did not multiply by the number of turns.
Which one?
The first and the second one. You just multiplied the 4.4 multiply by the flux, multiply by the kW, multiply by the 50, and I don't see the turns. So.
Now remember, the turns is that one. The number of turns per phase is 12 times 6 times 40 divided by 1. That gives us the 2,800.
Oh, okay.
All right.
Okay, thank you.
And then now for square three phase, is that 2,800 divided by 3. That gives us 555.62. And therefore, S is 3 times V times I, which is 48.118 kVA. Anybody got a question about that?
Sorry, sir. I have a question.
Yes.
When you are using that equation for E, the one with 4.4, isn't it when you only use tens instead of conductors?
Yes.
So what you calculated, the 2.8, the 2,800, what is it? Is it number of tens or number of conductors?
Number of conductors. No, it's number of turns. Remember, there's 12 slots, each with 6, what is it now? Times 40 turns. So there are 12 slots with 6 conductors per slot. And then we've got 40 turns. If we multiplied that by 2, then we would have gotten the conductors, and that would have been then 2.22.
Okay. So
Okay. Right, let's go on to number 3. There we have the number of slots per pole per phase is 3. And then the number of slots per pole is 18. And therefore, our slot angle is 180 divided by 18 gives us 10 degrees. It's coded by 2 slots, therefore epsilon is 20 degrees. And then if we calculate KD, we get 0.9899. And cos of KP is cos of epsilon divided by 2. That is cos of 10, that gives us 0.9848. The winding factor is the product of the 2. And then KD, for the third harmonic, it is N times G dash, no? So that gives us 0.9107. Yeah. And remember that 30 there, because it's 3 times 10. Okay? And then KP is cos of 3 times 20 divided by 2, which gives us 0.5. And therefore the winding factor is 0.455. And then E is the square root of 0.9748E plus 0.455E. And if we get the square root of that, then we get 1.076E. Any questions there? Right, so we go on to number 4. Everybody happy so far? If you're not happy, I don't care. Okay. I said if you're not happy, I don't care.
You're moving very fast.
Hi, you're a very slow learner, man. Remember, I'm recording this so you can go after it again. Once I'm finished with this session.
So it means we will be able to see those papers as well?
Yes. Okay, for number 4, it says G dash is 9. And epsilon then, because it says the slot, the coil is covering 8/9. So 1/9 is left. That means it's 180 divided by 9. That gives us 20 degrees. And psi is also 180 degrees because it's the number of coils per slot. That gives us 20 degrees as well. So then KD is sine G dash psi over 2 over G dash sine psi over 2. If we stick the values in there, we get 0.6399. And Kp is cos of epsilon divided by 2. That is 0.985. And therefore, the winding factor is 0.630. Everybody happy with that? No coughing is allowed, man. You put your arm in front of your face. Okay, Toby, I'm going to admit you now. Okay, number 5. Number of pole pairs is 3, frequency is 50 Hertz. Number of slots per pole per phase is 4. And the induced EMF per coil is 25 volt. And we have a full pitch coil. So therefore, G is 180 divided by number of poles. 2P. So that means, what have I done here? Just read the question for me. Oh, okay, yeah. G is the number of poles per pair, né? So it's 180 divided by 12, which gives us 15 degrees.
Yes, that's correct.
Got it? Now, why all of a sudden it doesn't look right? G is the number of slots per pole. So that shouldn't be 12, no? Can you see that?
Yes.
It must be by 6. You agree? Because G there, G is the number of slots per pole.
Per phase.
It's already given. It's already given.
It says there G dash is 4.
Yes. Which is our
Yes.
slot per pole per phase.
Yes. So if you now times P by GP, then we get S. But we interested in what is G, né?
Yes.
So that we can determine the slot angle. So that means it's 2 times 6. 2 times 3, sorry. That becomes 30 degrees then. You agree?
Sir, we can't see what you're writing anymore now.
No,
No, sir.
We're using G dash, and it's
Yeah.
already given us 4.
So the way you were doing it before, it was correct.
G,
Our G is given. G prime is given.
yeah.
G prime is given, we're looking for G.
We don't
No, we
need
don't need
G
G.
if we have G prime. We only need G prime, which is given, say.
Yeah,
Hmm.
E prime times.
And everything that it did is correct.
Yeah, but now remember, yeah, you're right. Because we are looking for what is the slot angle. What confuses me is this G. It should be T.
Slot angle.
The slot angle is because it's 180 divided by the number of poles.
Oh, yes.
Number of
So you calculated S. So you calculated S, isn't it? You're given G prime. You're
Yeah.
looking for S slot. You said 6 times 3, then you multiply by the 4. You got 72. So now you say 180 divided by the 72 slot. 72 divided by the number of poles, which you got the 15 degrees as your angle already.
right. So then we can calculate KD. That gives us 0.9577.
Yes.
All
Yes, sir,
right.
that's correct.
Yes.
And then E is 0.9577 times 25 because KP is 1. So that gives us 23.942. Then it says it's coded by 2 slots. So therefore, KP is now epsilon over 2, which gives us 0.9659. And since we've already got KD, the new E is going to be 25 times 0.9572 times 0.9659, which gives us 23.126 volt. Okay,
Yes, sir. Yes.
great. Number 6.
I have a problem with number 4.
Number 4.
Yes.
Why? What is the problem?
Number 4, our G prime.
Yeah? What was it?
Our G prime is 9, right?
Yeah.
Of which our but our the angle that 180 over 9.
Mm.
Is it a single phase or is it a 3-phase? The question.
It's a 3-phase.
It's a 3-phase, but the way we are treating it here, if you divide the 180 by 9, it's like we are using single phase now.
Okay, just repeat the question again.
Yes, on the question, you didn't stipulate, you didn't say it was a 3-phase or a single phase. So because it's not written, we regarded it as a single phase.
Normally, I will specify it if it's a single phase. Otherwise, it's a 3-phase. We are working with 3-phase in advanced diploma.
What's that, Matt? What are you doing?
So can you please rephrase what you just said? You said if you don't stipulate it, we regard it as a 3-phase.
Yes.
Okay.
So did I say G dash is 9?
I know.
No. So you said 3 multiplied by 9. You said 183 multiplied by 9. Well, that was your angle.
It was my mistake. I'm sorry.
No. It can't be.
I'm sorry. You do the way you're doing it correct.
Okay, Posha, I understand. Mr. Leroux, what's the value of your angle there?
20 degrees.
20 degrees.
Okay, yeah, Posh, no, out. No, Posh, you must mute yourself now. You got me confused.
Hey, please don't confuse the people, women. Right, let's go on.
Yeah.
Is the answer at the end your KW, say?
Yeah.
You will only get that answer if you treated it as a single phase. But if you treat it as three phase, it becomes different.
All right, just read me the question. I don't
Portia,
know.
which KW? Because question 4, it wants the pitch factor,
Yeah. Yeah,
not the winding
I
factor.
went,
So you're looking for KP.
I just did it all so that you know, that you can see how it is done. Normally the factor then would be 0.985.
Because our G, we are given G, not G prime, right?
Okay. Yeah, that's why I said
We are given
G is 3. No?
yes, sir.
Okay, now G is 9. Do you agree?
Yes, sir.
All right, so that is the number of slots per pole. So your slot angle then will be 180 divided by 9.
Yes, then you get 20 degrees.
Okay.
Yes.
9.
That 9 is our G, not our G prime.
Yes,
Then
yes,
our
yes,
G
my bad.
prime will be 3, not 9.
Yeah. Okay.
That 9 is our G, sir, isn't it?
Okay, got it.
Then our G prime will be 3.
Yes.
Yes.
Okay.
So
Portia,
if we-
why are you looking for G
if we
prime?
substitute in the KD formula, sir,
We need G prime in the formula because KD says it's.
yes, we need G prime, not G, but in your formula here, you put back number 4. In your formula, you substituted with 9, not 4.
True.
Okay, sir, can you please, I don't know how you can do it. We can't seem to see what you are showing us or writing anymore.
All right. It says there G.
Check to see the KD formula, sir, substituted with 9, not 4.
Why should I use 4?
Why didn't you use 4? You used 9.
Yeah, it should be 3.
Very much.
Yeah.
Sorry. All right, then that will change.
Then calculate.
It will be 0.9598.
Okay. Right. And then
Yeah.
okay, then KW.
Your KP is fine. KW. Yeah.
Right, then it will be 0.945.
Sorry, sir.
No.
Can I get clarity on that? You're saying if you don't specify if it's 3-phase or single, we assume it as 3-phase.
3-phase. Yeah.
Oh.
Okay.
So my question is alternators always 3-phase or?
Yes. We are working. Can you remember since we started machines 3, we said now we're done with single phase.
Okay.
So from now on, if I specify single phase, then you must do single phase. Otherwise, it's 3-phase.
3-phase. Okay.
Okay. Right. Then look at number 6. It says G dash is 4. It's sorted by 1 slot. Therefore, epsilon is equal to C. To get the slot angle, we have to use G and that is 3 times 4. So slot angle is 180 divided by 12. That gives us 15 degrees. And then if you calculate KD and KP,
This is a disaster.
that baby of yours apply to the course.
Guys, please, if you know that there's someone coming where you're sitting, can you please just mute yourself? You know, if someone is coming, you just mute yourself, then we can see you. It's fine.
This is a
Right. If you look at question number 6, they want it for the fundamental and then for the third harmonic.
Yes, sir.
So there you can see how it's done. It's basically all of them are the same. And 7 is the same as well.
open.
So hopefully you will understand how to do this now.
What's a teenager?
Something again with this question number. Number 6.
So I think we didn't do 5.2.
Which was that?
5.2.
Yeah, I did it. You didn't see it. Have you got it?
Yes, thank you, sir.
Okay, doc. Right, this concludes our chapter on KD and KP. Let's start with the trouble.
What is the
Which
trouble?
number 6? Something.
There's no 6. I think I skipped a number.
You skipped number 6.
Yeah, you skipped number 8.
Number
Yeah.
8 is the same as question 4.
Yeah, they're all basically the same.
Number 6.
Sir, can you please do question 2 again? I didn't get it.
Joe.
And I don't have number 7 on my file.
Right, okay.
There's something that is. Which one number 6?
I've got number 2.
Number 6.
6.
That's
Your
it.
That's number 6.
Yes, number 6.
It's number 2.
Have you got it?
Number
83.
Please, number 2, please.
Yes, number 6.
No, I took it off. I don't want them to see. So,
Which part of number 2?
Sir, can I just ask, with all these questions, if they are always saying, like if they say full pitch, we always regard the KP as 1.
Yes.
True.
Okay. Can you please explain because we given the number of conductors and the turns. There's a formula that you can use where you use the number of conductors and the one that you use for the turns. I just want to, can you please explain that to 2,800 how you got it again?
That is 40 turns for each coil, and there are 12 slots with 6 conductors in it.
Yes, sir. Okay.
Mister, what is that 6 there?
Pardon?
Because here, the 6 there, at 6 poles, but you're saying 6 conductors.
There's 50 conductors.
No, 40. 47. If you are 2 conductors, then 1 turn is 2 conductors. There's a conductor and there's a conductor. So that's why we say it is 2,22 KD, KP. And then remember the transformer formula? Where we had turns and it was 4.44.
I must do the same.
You are becoming slowly a picture again.
Right, then we go on.
No.
Yes, please. Yeah.
Yes, you can go on, sir. I think I would do it and then I will get back to you.
All right, then let's look at question 9.
Yeah, this is.
It gave us a graph there. Yeah, I've used the scale of 2.5.
And I'm open to check it out.
2.5 millimeters is equal to 1 volt.
Mr. Leroux.
Yes.
Mr.
Leroux. Yeah.
So is it possible if you can kindly ask the other people to turn off their mics? Can't hear you.
I'll mute them. Okay. Right. Now look at question 9. It's got a field current from 0 to 14 amps. And the voltage goes from 0 to 300. So that doesn't really matter what your scale looks like. And on the other side, I've got another scale, the short circuit current against the field current. Do you see that? All right. Now, will you be able to draw the graph?
Sir,
Yeah.
if it happens that we write at campus, is it okay if we bring our own graph paper? Because I find it very easy to use graph paper than to draw from scratch in order to save time.
Now what I'll do, I'll ask the exam office to give graph paper. Because
Okay,
you're not
thank
allowed
you.
to bring in any paper at all.
Oh, okay.
Okay.
Yes, sir. Thank you.
All right. Now, once you've drawn the graph of E against IF and I short circuit against field current.
Say,
Yeah.
your E. I don't know if it's mine that is wrong or it's yours.
Why?
When you calculate your E on top, it's VT plus I times Z, right?
Yeah.
And when you substitute, are your values correct there?
Yes. Remember the power factor is 0.75. Leading.
Yes, and the angle which give us what? 40 something.
Yeah, 41.4.
41.4.
Yeah.
But I'm getting my voltage as for 465, not that one.
Nope.
I'll double check. Maybe it's mine that is not correct.
Let's look. 250.
It's probably the 440. She should have divided it by the root 3. Maybe. Yeah, I think that's the problem.
Oh, mine, I'm always using them in phase.
No.
I'm always using my values in phase. I don't use them in line.
No. Remember, again, all the values always are given line. I will say if it's per phase.
They are always given in line. You say
Yeah.
them you say it when they are in phase, right?
Yes, I will say voltage per phase or voltage line. Okay.
Not clearly this time.
Right.
Oh,
Now, everybody happy with the impedance method? Remember your ZS that you calculate. They must be at the same excitation.
Yes, that one I got it correct, but the only one that I'm concerned about is the E when calculating the E.
Yeah, that must be phase.
Yes, mine is in phase. Can you please punch it again on your calculator, say?
Please punch your calculator, say. I think your E is wrong. The E is supposed to be 467.
Let's see.
165 point something, yes.
39.4 at an angle of 41.4, and then 6.35 at an angle of 87.3 times plus 218.
The angle, is it negative, sir, or positive?
Positive. Must be positive.
No,
It's
it's
a
positive.
generator.
Yes, but you didn't add that 254 point something.
I did, woman. I just showed you.
Sir, you are correct.
254.
Yes, sir, you're sir, can I,
Yeah.
sir, so how much is your tolerance range? Because your answer is necessary because I'm
working to 3 digits normally.
you round off to the, because you round off to you don't put decimals in your answers, right? So they differ a bit from mine because I got 219 instead of, because I punch everything as it is and then I only round off on my final answer.
Okay, that's fine. The method is the thing that counts. If it's 220, I'll probably mark it right. If your method is right.
Okay. Okay.
Sir, can
Yeah.
I ask something? I see when you calculate your beta,
Yeah.
you take RA, the weight is 0.3.
Yeah.
You are not supposed to divide that 0.3 by 2 because they say resistance of the armature between the terminals.
Okay.
Or you take
No.
it the way it is.
No, that must be then divided by 2.
Yes. Can you
Yeah.
correct it?
Okay, I'll correct it. But your method should be fine. Now the angle becomes, what's your angle?
It's 88.657.
Ah, woman, now you're going to kill me for 1 degree.
No, yes, because
okay. It won't make a big difference.
Mr. LaRue.
But it's a lag, it's a lag.
Yeah.
Mr. LaRue, you say that the scale of the graph doesn't matter. But when I was comparing my answers with another person, like it made a difference. So what is the tolerance range between like the amounts that we get off the graph and especially when it comes to the voltage regulation? Like what is the tolerance?
I've used my ruler to draw the graph.
Okay.
So again, if your method is fine, I don't care. If you get 15 or 16 or 13, it's fine.
Okay, thank you.
As long as I can see your method.
Okay, thank you, sir.
Okay, and then
That
for
is
the
fair.
Rothbard method, yeah. Was there a question? Okay, to determine the Rothbard EMF is V plus IARA cos phi. Just arithmetically added 254 plus 39.4 times 0.15 then times 0.75. You get a value. Then you go to your graph and across and down so that you can find what is the Rothbard excitation. All right. And the short circuit at 40 amp, you go across and down so that you find what is the excitation necessary to determine, to give you 40 amps. And that was 6.8. So you add the two and you get 12.76 at an angle. We don't worry about the angle. So then you go to 12.6. No, 12.8, sorry. You go up, you go across, you find the voltage is 335 volts. And therefore your voltage regulation is then 335 minus 254 divided by 254, and that gives you 31.
Sir?
Yeah.
There at when you're calculating the F-res,
Yeah.
I noticed, I'm not quite sure because it's not clear, but at the angle, you minused instead of adding, because you said that the power factor in the question is leading.
Leading. Okay. Sorry. That'll make
So
a
the
difference. Yeah.
answer becomes different. It's actually 5, I got 5,845.
All right. Let me just see quickly.
Approximately.
7.2. Hang on. 7.2 and 6.8 at an angle of 41.41. Oops, it becomes more. I swear.
So did you say 90 plus?
Yeah.
Because I think you just.
Yeah, that's why. Alright. It's 131.
Yes.
5.8.
Yes, sir.
Okay, my bad. So you see, you must be very careful. All right, and remember, we don't worry about the angle. So now you go to 5.8 and you go straight up. What did you get the voltage there?
221.
Huh?
I got 221.
221. All right,
Yes,
yeah,
that's what I
it depends. All right, so whatever you get.
My voltage regulation is 13.27%.
Yeah. And, all right. That you say it's 221.
Yes.
Then it must be negative.
Yeah, it is negative.
And that gives you minus 13.
Yes.
More or less. Again,
Yes, sir.
I want you to get the method right. I'll look at it and I can see if there's a mistake there, depending on whether you understand it or not. Okay.
Yes, sir.
Sir.
Sir, can I ask you?
Sir. Sir. The answer, I think, is correct. Remember, leading power factor, your E must be greater than, it must be less.
Yeah. That's right.
Less than V. Yeah,
Yeah.
it's correct. You were wrong.
Yes.
Yeah.
Sir, can I ask?
Admitted, woman, I'm sorry.
Sir, can I ask you something?
Yeah.
So what is the purpose of us calculating voltage regulation in practice?
Because if you start the generator and you must know more or less what is the voltage going to be. So then you can see, all right, it's close to tolerance. And remember, the actual voltage regulation lies between these two values.
Mm-hmm.
So that's just part of your machine design.
Yes, because the reason why I'm asking this is because in certain questions, I would get my voltage regulation to be something like 80%, which now I'm getting something like 13%. So it's kind of confusing for me. So what exactly is the significance of calculating voltage regulation? Should it be as less as possible, or should it be lie as high as possible in terms of percentages?
It will lie in between these two values. The one is optimistic and the one is pessimistic. So,
Okay.
I really can't tell. Because on full load, that is what your voltage should be. If you have 254 volts, you should get more or less 218 volts. And you see this one for res, you get 221. So between 218 and 221, it's more or less the same. Okay.
Okay.
But they say normally
Yes,
the
sir.
one is pessimistic, gives a lower value, and the one is optimistic, gives you a higher voltage, a value of voltage regulation. Okay, question 10. That's a bit of a tricky one. It says there, your excitation to give rated voltage, 37.5, and the excitation that gives you full load on short circuit is 20. So that gives you 54.83. And if you look, what is your voltage? Could be 750, 7,500 or 7,600, more or less there. Get the phase value, divide by your voltage, and you get 13.94. Now, the impedance one. This is where it gets tricky. If we assume that 6,600 volt is 1 per unit, and 37.5 is also 1 per unit, because that gives you 6,600 volts, and the field current, your short circuit current is 20 amp. So if we applied 37.5 amps instead of 20, what will the voltage now be? It will be 100 divided by times 37.5 divided by 20, because it's increasing, né? That gives us 187.5 or 1.875 per unit. Then your impedance will be V over C over I short circuit. So that means it's 100% or 1 divided by 187.5. Now, this is actually IZS. That's your volt drop. That gives you 0.533 per unit. And at an angle of 0.6 lagging. Nah. So therefore, E is 1 or 100 plus 53.3 at an angle of 53.13. Then you will get 138.7, or if you work in per unit, you will get 1.387. And then the voltage regulation is 38.7. It's 1.387 minus 1. Or if you worked in percentage, it will be 138.7 minus 100. And then you get the percentage. Are you dumbfounded or what? You understand it?
Sir, can I ask you something?
No.
Sir, I see that when you calculated your E, you didn't put in beta, and beta in this case should be 90 degrees.
No, no. Here we have our IZ. That's the volt drop that we calculated, which is 53.3%, which is your angle 90 minus your 36.686.
Okay, sir, thank you.
Okay. Then the next one is number 11. Basically the same. All of them are the same, and if you can do one, you can do them all. Just remember your impedance, when you calculate it, it must be at the same excitation. So if you look at 778, the voltage was 4,900. That was the line voltage. So if you divide by square root 3, then you get 3.63. And R over Z, you get 86. And then E, get 6030.8, and that voltage regulation is 58.27. Again, for Rotherham, 381 plus 778 times 0.2 times 0.8, that gives you 3935. So then you go to your graph and you look 3935 and you get 4.8. And your short circuit one, I said,
With 3935, what's
huh?
With 3935, your
Voltage.
IF is what? Yes,
That's your
the IF,
Rotherham
what
voltage.
is it?
That's your Rotherham voltage.
Yes, with your voltage, you got 3.95 kilovolts, right?
Yeah.
And then the current, what is it?
778.
Okay.
And that gives us, sorry, 5. 5 amps was 778. And then if you add them, you get 8.77 at an angle, which we don't care. Then you go to 877 and you go up and you find that the voltage is 7,000 volts. Now remember, if this is line values, then you can use line values. Then you can say 7,000 minus 6,600 divided by 6,600. That gives you 60%. Or you could have said divide by square root 3, all of them, and at the end it doesn't matter. You see?
So your last
Divide 7,000 divided by square root 3, 6,600 divided by square root 3, divide by square root 3. It comes down to the same thing.
Sir,
Yeah.
you're confusing us. You said to us we must work phase. Now you are using line. Then you say at the end we must do we must divide by root 3.
No, I said if you use line values, you can use that. Because this is line given, and we are working here line values. You see? All right, so then we can someone net use the same voltage there, 7,000, which we got there. Or if you wanted, you could say, all right, that's 8.77, and then all these values, if you divide it by square root 3 to get to per phase, then it wouldn't matter. Because all the voltage, in the end, you're going to divide by square root 3. Okay.
Yes.
Hi.
I know this is higher grade.
Sir, this question, I think you are wrong because your F Roth, you say it's 4.8.
Will be 13 points.
I disagree.
Why?
Yes, I also second
Your
her as well.
F is 13.6. 13.7.
Yeah?
The
How
F
did you
is
get E Rotherham? What was your Rotherham voltage?
Around 12.
What was your Rotherham voltage?
Sir, you
yeah,
mixed.
My bad.
was 7.8.
Yeah, wait a second. You see, now I made the same mistake as you guys. I use a phase value here.
Sir, why? Sir,
Yeah.
you are mixing phase values and line values. Why?
Yeah.
Why?
No, that was a mistake.
You mixing. Yeah, calculate.
Say,
Hey,
what was your F, Rod?
6,724.
The F, Rod, say, the current.
I'm gonna tell you now. 6, 7.
Again, he's still fixing.
7.8,
Yeah,
right?
yeah.
And then your F short circuit is what?
5.
Was 7.
Please give Sir a chance to fix it. He's going to say yes. Please. Sir, fix after you are done. Tell
No,
us.
he's not gonna say yes. He's reading from his notes.
Yeah, but I'm
No,
changing.
the thing for you see, he's erasing things because they are incorrect. So you are asking him what? There is no
And
value
give
there.
him time to recheck after.
Yeah, please, man, please.
6,700 is 7.5. 7.5 with an angle of 0 plus 5 angle 53.13. Right, let's see. 7.5 I get 11.23. Your full load current was 778.
Yes.
So what was your excitation for that? 5.
2,829.
No, 5 is dead. From your graph.
5,
Even. Look at your graph. The ones that you were given, the data. Is there 5 and 778?
Yes.
Okay.
Oh, yes.
And what was our power factor? 0.8 or what?
0.8. Yes, 0.8.
Okay, so that means it's 90 minus 36.87, no? And then you get 11.24. Okay, so 11.2 is 152. 380. Yeah, man. Oh, this scale is different. 50. Um, 52. 7,600. You agree?
For what's the E-race?
Yes, 11.24, then you get 7,600.
No, I got 4,56 kilovolts.
Then you're wrong.
He's working with, sir, you are working with lines. Go, we want to check the final answer. Voltage regulation.
Okay.
It won't be the same.
Minus.
Yeah, but if you converted everything to lines, it should be the same.
15.1.
Again, for now, you are not converting. Let's wait and see.
Huh?
All right.
What did you get your percentage?
19,68.
Yeah,
close
same
enough.
close by.
Yeah.
Yourself, what did you get?
15.2.
Ah, you are out.
Yeah, you're incorrect, sir.
Said that if you get 15.813 is right.
Okay, again, just look at your method.
You just want to stick to one thing, guys. He said it from the beginning.
Pardon?
Let's continue. No, I'm saying they're saying that 15.2 is wrong, but you said it. You said from the beginning. You said that if you get from the range of 15 point something, 13 is still right as long as your method is right.
Yeah, yeah. It's close enough. All right, let's look at the last one. Or the second one. No, it's the last, second last.
Oh, you ending in voltage regulation.
Yeah.
Okay.
Right. Then, again, it's the same story all over. But let me ask you this. So, do you want to class every night? Till we catch up?
No, sir, I don't think we should do it every night because I think people are going to need an opportunity to do the tutorial questions so that as you are explaining all your answers, everyone is on board. So I think every 2 days or 3 days is okay.
So Wednesday night?
Yes.
Okay, sir, but
Wednesday. When is today? No, not Wednesday.
Okay,
It's
sorry,
too
guys.
early.
Sorry, guys. Can I ask sir one question?
Yeah.
Yeah, going forward, I mean, like these chapters, we were before lockdown, we were attending physically at the campus, and then most of us, I think, we were on the same page with you on that. However, there is other chapters which we never did with you. Can we please maybe revisit those chapters before continuing with everything?
Well, you see, these questions that I sent you covers all the chapters.
Yes, I understand this, all the chapters.
But look at, did you look at the videos?
Some of the videos I couldn't access actually.
Just find out how to get to those videos because all of them should be available.
Okay, I'll try to check them and I'll see what to do.
What I'll do is I'll look at the links again and then I'll put it on.
Okay.
Is that okay?
Yes, thanks.
Or if
Sir,
you
I think sir, Warren is telling the truth because there is no way we can ask questions from the YouTube there. So it's best if this one of design and silent poll. It's a problem when coming to phasor diagrams. So it's best if you can do it like this so that we can ask questions.
Okay, I'll do that.
Yeah.
All right,
so I was thinking, okay, sharp.
So for next time, which is when is that going to be? Can we do that on Wednesday?
Yes, it's okay.
After 2 days, it's okay.
So to tackle what?
Sir, yeah.
Then
I think alternators.
Explain salient poles.
Oh.
Then you can carry on in the meantime.
Okay.
Then I'll start with the phasor diagrams.
Okay.
Okay.
Yes.
Yeah. You're doing very well.
What?
No, we're saying it's fine, sir.
Pardon?
It's okay. We can proceed with the other chapters on Wednesday.
Yes, fine. Same time. 5:30, I'll log on and then you can start joining.
Right.
Silent poll, Wednesday.
Yes.
Okay.
Then I'll put it on WhatsApp again. What is the link? And then we'll do that.
For the videos, sir.
We are following. We are following.
Can I ask you one question there? For if I have these two graphs, the OCC and
short circuit
SCC, if I have to calculate the ZS, I have to check the full loop current to project it towards the short circuit current and then take it to the OCC.
Yeah, you must use the same excitation. So if you take the full load current,
yes,
you go across, let's say it's 40 amps, no?
Yeah.
And then you go, no, that's too little. Let's make it 70, no? Then you go across.
All right.
And there's your excitation for the short circuit.
Yeah.
And that one is your Rother. Is your EMF. That's the excitation to give that voltage at short circuit.
Yeah.
And then
So
you
that
calculate
voltage,
Z.
that's the one which I used to calculate the ZS.
Yeah.
That voltage.
That's right.
Okay, thanks.
Okay.
All right.
All right, I'm gonna make this video and then I'll post it.
Sir, please, can I just ask, you said on Wednesday you're covering what?
The phasor diagram of synchronous machines and synchronous motors as well.
Okay, sir, thanks. So are you gonna upload this video now in our group?
Yeah, whenever I'm done, I'll upload it.
Okay, thanks.
Okay. And I guess that don't forget those links for the videos on YouTube.
Okay, I'm gonna look for them now.
Okay, so thanks.
Okie dokes. Have fun.
All right, bye.
Bye.